This is like basically the final chapter. We'll see what we have time for with chapter 12. We only like barely cover a couple of sections in chapter 12 usually. But chapter 10, acids and bases. We have 3 full lecture days scheduled for this, so it's kind of a big deal. But before we get to the acid and the base part, let's talk about a fun hike that is actually in Arkansas. So I'm going to show you 2 hikes or 2 portions of hikes. And these are 2 of my favorite in Arkansas. I think the Indian Creek one, Eye of the Needle that I showed you a while back, that one's my ultimate favorite, but this one's one of my favorites. It's called Hemden Hollow, and it's in right on the Buffalo River. So there's 2 ways you can access this trail, a hard way and an easy way. There's a place called Compton, the Compton Trailhead. Okay, that should be black. So if you look that up and you look up Hemden Hollow, you can hike that way. And if you do that, it's a down and then it's a back up. And it's down almost the whole way there and then it's up the whole way back. So that one's a little more difficult. But at the end, when you get down, you see this beautiful waterfall. It's really high, really tall. Now, if it hasn't been rain, if you go in like a really dry season, it's going to be a pretty pathetic waterfall. But if you go after a really big rain, or like recently, just with the rain we've had, you would probably see a pretty good turnout on the waterfall. And then people can hike like back up in here in this area of the rock and stuff. So that's cool. The other way you can access it is very pretty. The other way you can access this is if you're floating the Buffalo River. You can park your canoe or kayak or whatever. I forget the specific area, but if you float between, if you put in at Still Creek and get it out at Cowles Landing, those 2 spots, then you'll pass the area where you can park your canoe, kayak, and then you can hike. It's way more flat. It's just kind of an in and out to the waterfall and back out to the river. So that's a really fun trail to hike. The next one is called the Lost Valley Trail. This looks really creepy, I know, because I took this picture from the inside of a cave. So the Lost Valley Trail takes you to a cave. And some people are like, yeah, to your death. No, it does not. It's a really cool cave, though. If you get claustrophobic or you just don't like dark, tight places, don't go in the cave because you can hike a ways back in the cave and it gets really narrow and really small. You need a headlamp if you go. Take a good headlamp. And there's a waterfall inside the cave. Okay, Google it, look it up. It's awesome. A waterfall inside the cave. So anyways, this is called the Lost Valley Trail. It's a really beautiful trail as well, also in the Buffalo River area. Grant says, if you're ever in the Mulberry area, you should check out the Devil's Holler Trail. Okay, thank you, Grant. I'm going to look that one up. I'm going to make a note of that. I'm going to write that down right now. Devil's Holler Trail. I've never done that one. How long is it? Do you know? I know the mulberry is like really good for floating. I know my husband went and floated that like in March one year. It was freezing cold, but he like had the time of his life. So, all right, that's all my hiking info for today. We are now going to talk about acids and bases. Okay, so obviously, if you say the word acids, people think of different things. So we're going to clarify the kind of acids we're talking about for today's lecture are not recreational. Okay. We will actually talk about some sort of organic acids like citric acid and lactic acid. You guys probably know what lactic acid is all about. And then acids that are used in clinical settings, biological acids in our body, and in the laboratory setting as well, and just how acids and bases react. So first off, let's just go ahead and define what an acid is. It is a chemical that donates a proton, which is essentially, if you look right down here, a hydrogen ion is a proton. Okay, remember a hydrogen atom has 1 proton, 1 electron. So if we draw a picture of it, it would look like that. And this is the plus charge, and then it would have 1 electron on the electron cloud. Well, if it gives away that electron, all that's left is a proton, right? So that's why we kind of just interchangeably use the word proton for a hydrogen ion. So donates a proton, which is a hydrogen ion, to another chemical. All right, that is an acid. It's going to give away a hydrogen ion. So that means it has hydrogen as part of its chemical formula, and it has to have a certain kind of hydrogen that is able to be given away, okay, broken off and given away. So because of that, sometimes acids are called proton donors. Like, is that right? Proton donor. Okay. So proton donor. That's kind of the nickname for an acid. Oh, sorry, I'm catching up in the chat. Yeah, I will definitely post the recording. For sure. Always do. All right, so let's look at an example of a chemical, an acid, giving away a hydrogen ion. In aqueous solutions. So I'm just going to write AQ because we know that's the abbreviation for aqueous. So what does that mean? In aqueous solutions, that means in water, okay? If you're doing something in water, water is usually a part of everything. You're in an aqueous solution. What happens here, so if water is present and we have this acid right here, HCl, you guys are familiar with this acid, hydrochloric acid. It's in our stomach. It's important for a lot of reasons. The hydrogen ion is going to be given away. It's going to be donated by HCl to water. So it's going to be donated to water. And it's going to create what? When water accepts that, here's what we create in the brackets over here. Water with another hydrogen added. So we call this hydronium. This is actually one of the polyatomic ions that you should be familiar with if you took the time to memorize those earlier in the semester. So hydronium is abbreviated H3O+. But it's not attached very strongly, okay? It's like, I'm on here, but sometimes it can hop right off in aqueous solution and hop back on and hop back off of water. So because of that, sometimes, well, all the time, pretty much H3O and H+ are used interchangeably, okay? So if I were to ask you in any sort of acidic solution, what is the concentration? Like if I ask you for the concentration of H+, that would be synonymous with asking you what's the concentration of H3O+, okay? They would be equivalent, okay? So we use H3O+ and H+ interchangeably, all right? If I'm talking about how acidic something is, I can measure the concentration of H3O+ or H+, same thing, all right? I know they have different formulas here, but I want you to think of them synonymously, all right? And then what's left over from the acid? Just have that chloride anion is left over. All right, once the acid gives away a hydrogen, what's left of the acid is still present, so we have to write it into the equation as well. All right. Okay, question so far on what an acid is and what an acid does. We're going to look at some examples, some more. So another example of a different acid, what happens when you dissolve an acid in water. I want you to look at these based on what we just talked about. So we're not considering water to be the acid in this equation. So we're considering HNO3. Anybody know the name of that acid? HNO3. You've got nitrate is the polyatomic with a hydrogen added on, so that makes it nitric acid. So if this one is the acid, and we know acids give away hydrogen, could you write the products? The H+ is going to be given from HNO3 to water. So then write what's going to be left after that trade happens. You should have NO3. It'll have a negative charge because it was neutral on the other side. And when you give away a hydrogen ion, now you just have the nitrate anion, which has a -1 charge. Plus, you will also have what we wrote above, H3O+, the hydronium ion. Okay, does that make sense? So the H+, the hydrogen ion, attaches to the oxygen on water and makes the H3O plus, okay? I want to scroll back up so I point that bond out. I think I circled it, but you see how the hydrogen ion, it's attaching to the oxygen. See how the oxygen had 2 lone pairs over here? And then one of those lone pairs was used to create the bond, okay? Because any chemical bond has how many electrons in it? This bond has 2 electrons. Any bond represents 2 electrons. Those electrons have to come from somewhere. They can't just come from thin air. Well, the hydrogen has nothing, no electrons, okay? The hydrogen ion, it can't donate any electrons to the bond. So both of these electrons come from the oxygen to form that bond with the hydrogen and make the H3O plus, okay? So that's what happens. That's how it's traded. That's how oxygen or water receives the hydrogen ion. It says you can also omit water and then just convey the same thing by writing the reaction for the dissociation of HNO3. So we know water is usually present. Okay, acids dissolve in aqueous solutions. Acid-base reactions happen in aqueous solutions. So sometimes people will just write HNO3 dissolving to H plus and NO3 minus, okay? Remember how we said H3O plus and H plus are synonymous, okay? Same thing. So we just call this the dissociation. This acid right here is just disassociating or simply dissolving into its ions. All right. So if we had like, if it's a really strong acid, if we had like 1 molar of this and starting out we have 0 of these things, when it's all done, we would have what? 0 of that left and 1 molar of these, both of these things. Does that make sense? Initial and final concentrations, because we're going to learn how to calculate pH based on the kinds of acids we have and how much H plus we create in the solution, or H3O plus. But we'll get to that later on. All right, questions so far? Questions so far on acids? Let's keep going. Many polyatomic ions can exist as acids. We just looked at the example of nitrate existing as an acid. Nitrate, when you put a hydrogen on that, is nitric acid. Okay, but several of those polyatomic ions have multiple hydrogens on them. Okay, so they could donate more than 1 proton. Okay, so they could donate multiple protons. So I know Cl minus is not a polyatomic, but this is hydrochloric acid. But I just want to point out how we name acids that can donate more than 1 proton. So any acid that can only give away 1 hydrogen. So the acidic hydrogens are the one in red. All the acidic hydrogens are in red. So if an acid just has 1 acidic hydrogen, we call that a monoprotic acid. Mono meaning 1, protic meaning it can donate 1 proton. Okay, nitric acid is also a monoprotic acid. So you see the Lewis structure for this. Sorry, the lone pairs aren't written in, but that's also a monoprotic acid, just 1 hydrogen in there. But look at sulfuric and phosphoric acid. Okay, sulfuric acid, this is diprotic acid. Okay, it's a diprotic because there's 2 acidic hydrogens. And then phosphoric acid is triprotic, 3 acidic hydrogens. Okay. But what you need to know is acids always lose only 1 at a time. Only 1 at a time. So let's draw the different dissociations for phosphoric acid. Phosphoric acid is H3, PO4. So if we're starting with the fully protonated acid, and we have H3PO4, if it gives away 1, draw the first dissociation step. If it gives away 1 hydrogen, well, we're going to create that one. What's also left over? If you take away 1 hydrogen from over here, what formula do you have left? Somebody help me out.
H2PO4 plus the hydrogen ion.
Right. You have the hydrogen ion, and then you have H2PO4. What's the charge on this, Bailey? Or anybody?
Negative, right?
Negative. That's exactly right. Because these 2 things have to add up to the original, which is neutral. Does that make sense? Okay, let's keep going another step. Now let's just look at H2PO4. What would be the next dissociation if we were going to give away the second hydrogen? Well, we're going to create an H plus And then what else?
HPO4.
Yep. But what's the charge on that now? It was originally a negative. Give away one more positive. Maria says a -2. I like that. So you see how it gives away one at a time? One step at a time. You could even draw the next one as well.
So the product side will always, like, after the arrow will always start with an H plus.
It doesn't matter if I write the H plus first, Blake, or the phosphate portion first.
Okay.
Either one. Yeah, that part doesn't matter, the order, but it does create an H plus and then what's left over from the acid. Okay, so that's a little bit on acids that can donate more than one hydrogen. Now, I'll tell you this though, the first hydrogen that it gives away, so we'll call this step 1, and then we call that the second dissociation, the first dissociation second. This hydrogen will be more readily given away. That's gonna be, we call that the most acidic hydrogen, okay? The first one that it gives away, that's always the step that happens the quickest and the strongest, okay? After that, it's less and less easy to pull a hydrogen off the acids. Okay. All right. Next slide. If an acid has multiple hydrogens, how do you identify if it's acidic or not? An acidic hydrogen. So if I'm looking at a Lewis structure and I ask you, all right, which hydrogens on here are acidic? There's some that are and there's some that are not, okay? Sorry, let me look in the chat. So acids really want to lose the hydrogen. So if there is a negative ion, they will always lose. So like example, Bailey, I'm going to zoom in on, we drew this guy. This is a negative ion. Is that what you're talking about? And yes, this is still an acid. Okay. This is actually something that could give away a hydrogen or receive a hydrogen, depending on what it's in solution with. So that gets kind of complicated. So we could, I don't want to confuse anybody, but we could recombine the H plus and this and remake H3PO4. Okay, so in that case, it would be receiving a hydrogen. But it can also, like we wrote, it could also still give away a hydrogen. It could go either way. Okay, but how it's going to behave depends on what it's in solution with. If it's in an aqueous solution with a really strong base, it might act like an acid. But if it's in solution with a really, really strong acid, it might act like a base. Okay, there's some molecules, and we're going to talk about these. They're called amphiprotic. Okay, and again, it's kind of getting ahead of myself. I'm going to talk about what amphiprotic means in a few slides later. But there are some molecules that can give hydrogens or receive hydrogens. Did that answer your question, Bailey? But acids typically lose hydrogens. But again, it depends. We have different strengths of acids, and we're going to get to that as well. Yeah, you just wait. All right, let's go back to this. So only the hydrogens that are bound to electronegative atoms, okay, such as oxygen, fluorine, chlorine, are acidic. And this is particularly for acids that are inorganic acids. Okay, what does that mean? What is it? Does anybody know what the word inorganic means? You've heard of the word organic, okay? You can buy organic food at the grocery store. There's a whole field of chemistry called organic chemistry. What does inorganic mean? Grant said no carbon? Yeah, okay. It's we tend to use it as something that's kind of like it's no carbon is present in it. Things that have carbon present, we say they're organic compounds. So if there's no carbon present, it's called an inorganic acid, all right? But in organic chemistry, so these are compounds now that have carbon present. The human body is organic, a lot of the molecules there, everything has carbon in it. There, an acidic acid is usually bound to, I'm gonna write this little group, COOH. Okay, so I'm gonna put parentheses like this around because that's usually just a portion of the molecule. COOH. In chapter 12, you're actually gonna learn there's a name for these kinds of little groups. Anytime you see a group like that on a molecule, we call this a carboxylic acid, okay? This is known as a functional group, okay? So this is a portion of a molecule. It's not a molecule entirely in itself, usually. It's known, the name of it is a carboxylic acid, and this is known as a functional group. Chapter 12 is all on functional groups. You nurses will have to recognize certain functional groups. So let's look at acetic acid. Do you see a COOH in there? You also see other hydrogens. You have all these hydrogens over here on this first carbon, but the hydrogen that's on the COOH, that's the acidic hydrogen, okay? Remember, hydrogens that are bonded to just carbon are nonpolar and they're not going to be acidic. So if we draw out the Lewis structure for acetic acid, looks like this. All right, and I'm going to box in blue here. This is the COOH, okay? This is how they look. You got a carbon double bonded to an oxygen, and you got an OH group, all right? And it is, I'm gonna highlight, it's this hydrogen right here that's acidic. That is the one that's acidic. The other hydrogens are not acidic. So what does that mean? They're not gonna be given away, okay? These are not acidic. They're not gonna be donated. But
How
this
did
one
you
right here,
know that?
do what, Bailey?
How did you know that?
I've studied this a long time. No. So here it's a little more complicated. That's a complicated question. But if you want me to open that can of worms, anytime you give away a hydrogen, you leave a charge burden on a molecule. What do I mean by that? Let's redraw this without its hydrogen. Okay, now you have something like this. You got this big old negative charge on this molecule. Molecules don't tend to like holding negative charge, all right, especially organic molecules. But we have all these oxygens. Oxygens are very electronegative atoms, right? Where are the electronegative atoms on a periodic table? They're close to fluorine. So these oxygens, and in fact, because there's two of them on here, these oxygens can help handle that negative charge, okay? You're gonna learn the more you dive into chemistry, which some of you after this class are like, never, that will not be me, that electrons and charge can move around, okay? So this charge could actually jump between these two oxygens, and that can help this molecule handle the charge burden, sometimes what we call it. It's called resonance, okay? So anyways, that's why this hydrogen is the acidic one, because anytime, if you were to give away these other hydrogens, you're leaving a negative charge on a carbon, which is absolutely illegal, not okay, not gonna happen, okay? Electronegative atoms can handle the charge burden better than carbons can. Okay, there's much more to that answer, but it takes a little bit more time with chemistry to fully understand some of that. All right. Lactic acid. Which one is the acidic hydrogen? Let's draw that out. The very last one. You see a COOH group on there, a carboxylic acid. Boom, there, here it is. Okay. You see the carboxylic acid, so you can easily identify the acidic hydrogen, all right? Now, I'll tell you this, unfortunately in chemistry, you know, there's always things that bend the rules. I can't usually say it's always gonna be this way, or it's only ever gonna be this way. So in lactic acid, let me highlight, right? This is our acidic hydrogen. Sometimes this guy right here, because it's also bonded to an oxygen, could be acidic. Okay, so if you look up acidic lactic acid and you say how many acidic hydrogens have, it might tell you 2. Okay, because this second hydrogen is acidic as well, but the most acidic one is the one in the carboxylic acid. So I'm gonna box that in blue, the way we did on the first one. All right, so there's the acidic hydrogen on the carboxylic acid. All right, so that's the one that's acidic. And then sometimes this is acidic as well. All right. So lactic acid is important. Why is lactic acid important? My husband loves to tell me how sore he is when he comes home from a workout or the next day. Oh, my legs are sore. Oh, my arms are sore. Guys, you never say that, do you? I'm so sore. I just lifted so many weights in the gym today. Okay, so why do we, oh, hold on. I'm still confused on why acids want to leave their hydrogens. This is just, there's molecules don't have a feelings, Bailey. So there's not necessarily like a why or why. It's just what they do. It's just how they behave. The more you learn about acids and bases, the more you might understand that. I didn't mean to make light of that question. That's a good question, but there's not necessarily a straightforward answer on why. This is just what we've observed on how they behave. Does that make sense? Okay, I hope so. Science is rude. All right, citric acid. So here's citric acid right here.
They can, Whitney wanted you to slide up for a minute.
Oh, I'm sorry, Whitney. Yep, thank you. Right here. All right, good deal. So let's look at citric acid. So this is a little bit of a different representation of Lewis structure, but can you identify any carboxylic acids? Let's try to box them in blue as well. So remember, have you guys seen anything like this before? Kind of stick figure drawings of molecules. Anytime two lines come together, there's an understood carbon here, 2 or more. Okay, so there's literally carbons at all these little elbows. Okay, so now can you identify the acidic or carboxylic acids? Where do you have carbons and then an oxygen double bonded with an OH group also bonded? There's lots of them actually. Actually, I'll highlight these in blue. Right here, there's a carboxylic acid. Right here, there's a carboxylic acid.
That's hard to see, by the way.
Oh, it is. Thank you it's great on my iPad. It's terrible on okay, let's just go back to my original plan. What if I highlight it in red? Now can y'all see it? Not really? Okay, let's just don't highlight. What if I box it in like this?
Yes.
Okay. All right. Okay, these are all carboxylic acids. All right, so all these hydrogens are acidic. And citric acid, this guy right here, there is a hydrogen branch to the oxygen, so you might be tempted to think, oh, that one could be acidic, but it's honestly not. Okay, it's these hydrogens right here. I'm going to underline them. That are the acidic hydrogens. All right, so that's why I wrote up here. You got to focus on the carboxylic acids. All right, that one in lactic acid is kind of unique. Okay, any questions? So if I gave you a molecule kind of like citric acid, I said, can you identify the acidic hydrogens or tell me how many are acidic? You could look at that and tell me which ones are acidic. All right, so that's enough about acids for a moment. Let's talk about bases. I gotta be really careful in this lecture. I say the word acids like 1,000 times. Sometimes you can slip up on that word. Okay, when an acid donates an H plus, it has to give it to something, right? It doesn't just generate that and it doesn't just go into oblivion. Something accepts it, something receives it. So that's the base, okay? The base receives the H plus from an acid. So we nickname it proton acceptor. So we got a proton donor, proton acceptor. So think about when we had HCl earlier, and we said in aqueous solutions, what's going to happen? Also with the HNO3, we looked at an example of that giving away hydrogen. Water was acting as the base. Okay, we got water. When it receives an H plus, it makes the hydronium ion, so it was acting as the base. So What is the H plus likely to attach to on the base? Well, with water, we saw it was the oxygen, but what specifically on the oxygen? You guys remember? So here's water. What on the oxygen accepted that H plus? I pointed this out. Yep, Rachel said it. The lone pair, okay? I'm not gonna highlight anything anymore because y'all can't see it. Okay, lone pair. So what is it? The question here, what is H plus likely to attach on the base? It's gonna be electrons. Okay, specifically lone pairs. So what are two very common bases? Let's look at this. One very, the strongest base we know of is just OH minus, a hydroxide. This is hydroxide. Hydroxide, specifically an ion, okay? Now, this could come in the form of like, I mean, as a compound, it might look like sodium hydroxide, lithium hydroxide, calcium hydroxide. Okay, these are all strong bases. Yes, Molly, 2 seconds. I'll scroll right back up. But these are all aqueous, right? So these are all going to dissolve in solution and generate OH minus. Okay, so it's OH minus that's acting as the base. Let me scroll back up. Did you need me to go farther, or was that good, Molly? Okay. So how do these accept hydrogens? Well, OH minus is probably very easy to think about. If you draw the lone pairs on it, why is there a negative charge? Because there's actually 3 lone pairs here. Look at how many different options we have to receive hydrogens. All these lone pairs. Okay, so any one of those lone pairs can receive a hydrogen, an H plus. And we write the negative charge kind of overall. All right, another very common base would be NH3. You guys remember the name of NH3? It's ammonia. AMMONIA, not ammonium. Okay, that's NH4 plus, just ammonia. So let's draw the Lewis structure for that. There's a lone pair on the nitrogen. Okay, so guess where that hydrogen is going to go? Onto that lone pair. So if we were to draw simple chemical reactions, balance reactions for how these things receive hydrogens, if we just had like NaOH and we said, well, we got some acid here that's going to donate an H plus. So I'm just going to literally write H plus. How is this thing going to accept it? Okay. Well, you would this would disassociate into Na plus and OH minus. And so when you join OH minus and H plus together, because that's the base, so it's accepting the H plus, what do you make? What's OH and H plus make? OH minus and H plus.
H2O, water.
Boom, H2O. Now do you guys remember why in chapter 5 we call them acid-base neutralization reactions? When you're neutralizing something, what do we create? We're creating a very neutral compound, water. Very neutral. It's not acidic, it's not basic. Okay, that's why they call them acid-base neutralization reactions. All right, so that's an example. You could draw the same with ammonia, all right? I'm kind of out of space here, but you could draw NH3 plus H plus. What would you make? Actually, I am gonna write it in now that I said it. If you had NH3 and H plus, this one does not disassociate, okay? It's not an ionic compound, it's not made up of ions. NH3, so it's not gonna break up into anything. It's just gonna receive the H plus. What do you make when you do that?
NH4.
What's the charge on it? We have something neutral and we give it a plus charge. So overall, this thing has a positive charge. So this ammonium ion is what we make. Okay. All right, so this is a little bit on how acids and bases give and then receive hydrogen ions. I'm going to show you some chemical reactions in a moment, and you're going to tell me which one's the acid and which one's the base, based on what we've learned. So, look, I had those drawn right below. I had forgot this slide was on here. Okay, so what we just drew is actually all right here for you. But I do want to point something out on this. Okay, this is a neutral base, neutral starting out, no charge. Okay, it's just NH3. It's not plus or minus. And when we add the hydrogen to it, what did we make? Ammonium ion with a plus charge overall. So adding the hydrogen creates a positive charge on that compound. So bases always increase in charge by 1. Bases always increase in charge by 1. Look down here, same thing. Even if we start out with something that's not neutral, if we start out with something that's negatively charged, okay? So a base with a lone pair with a negative charge on it. When it receives that H plus, when it grabs the hydrogen from the acid, now we have something that is neutral. So if you go from a -1 to 0, did you increase in charge? That you didn't become positively charged, but you still increased by 1. Okay. Bases always increase in charge by 1. Doesn't mean they become positive, but they increase. Sometimes they do. Okay, questions on that? I want to point this out. Sometimes we abbreviate. I think I introduced this back in chapter 5. We abbreviate the acid as HA. Okay, so A stands for acid, and the H is just showing you the acidic hydrogen that is on that acid. So this is just a very generalized abbreviation for acids. And then what's always left over is the acid with a lone pair and a minus charge. Or I should say it decreases in charge. But we're gonna hit that a little more deeply in just a second. In fact, right now, acids lose a plus charge. They lose a positive, right? They give away a hydrogen ion, and the hydrogen ion is a plus charge. So they decrease in charge, which means things that are originally neutral become negatively charged. So for example, if you had an acid with a -1 charge, a very good example that we already wrote out earlier was H2PO4-. Remember when we were drawing the H3PO4, disassociating at every step? This was the middle guy. If it is an acid and it gives away a hydrogen, this is what we wrote earlier, how would I have a -2? Okay, acids always decrease by 1. All right, went from negative to -2. So bases, we said gain a plus charge, so they increase in charge. There's so many different scenarios you could write out with this. Neutrals become +1. That's what we saw with NH3. It's neutral and it gains a hydrogen, so it becomes NH4 +1. Okay, so it was neutral starting out, and now it's a +1. Bases with a -1 charge become neutral, okay, increasing in charge. It's just 2 examples. It's not all the examples, it's just 2. So these kinds of things should help you identify, if you're looking at a chemical reaction, look at how the charge is changing. That could help you figure that out. I think the next one I have is just a review slide, and then we're going to do a poll question. All right. So any questions on how the charge changes? Everybody got this written down? This is all very confusing right now because it's all just stuff you're writing on paper. So we're gonna put this into practice, and I think that should help you. All of what we've been talking about so far. Why are we talking about what acids and bases do? The goal of this, I want you to be able to look at any chemical reaction, and if it's an acid-base reaction, identify what is the acid and what is the base. Okay, we're having to start here today. The ultimate place where we're headed is in the coming lectures. Okay. We're going to talk about pH and how pH changes, because that affects the body in a lot of ways. Okay, you have a physiological blood pH, and it's very critical that your blood keep physiological pH. But you won't understand all that if we just start talking about pH. We have to understand at their foundation what acids and bases are and what they do. Then we can start seeing how they behave in chemical reactions and how pH changes and how that affects our bodies and all of that, okay? And the implications of that. So hang with me. If you have heard nothing of what I've said so far today, if you're still confused, just remember an acid donates H plus and a base accepts it. All right, that's kind of the summary. And this is just another example showing you with the labeled acid and base and how the charges change. All right. So this is the review slide. This is a summary of all we've talked about so far. Okay, so because of that, you guys remember back in chapter 5 when I said acid-base reactions, you can identify them because they produce water. I said you will know it's an acid-base reaction if it produces water. Well, that was a sufficient definition for back then, but it's not sufficient anymore, okay? I didn't lie to you. Acid-base reactions can create water, but that's not the only kinds of acid-base reactions. It's so we need to redefine them is what I'm trying to say. Acid-base reactions, now we can understand the reaction in which a hydrogen ion is transferred, okay, from one thing to another. Again, here's the review thing, then I'm just going to beat it. I'm just going to keep beating it. Acid donates, base accepts. All right, and it's the lone pair on bases. So if a molecule doesn't have a lone pair on it, can it be a base? No, it cannot. If you don't have a lone pair, you can't accept a hydrogen. You cannot be a base. All right. Okay. Again, this is kind of review. So this is really the slide I want to get to. We're going to put this into practice. Identify the acid and base in each of the following reactions. I'm going to do number 1 with you, and then we're going to do number 2 on a poll question. So number 1, we've got CH3NH2 and water. So looking at that, I don't know. They both have hydrogens in them. I know that the nitrogen has a lone pair. The oxygen would have 2 lone pairs. So I don't know right now which one's the acid and the base because both have things that qualify them. Could be either one. But when I look at the product side, I see CH3NH3 plus and OH minus. So you tell me which compound, the first one or the second one on the reactant side, gave away a hydrogen. Which one is the proton donor? Which one gave hydrogen away? Water. It was H2O, now it's OH minus. So this has got to be the acid because it donated the H plus. All right, it lost one. Over here, it's just OH minus. So what happened then, if that's the acid, this has got to be the base. And this lone pair grabs the hydrogen from water. The lone pair on the nitrogen. All right, so with the same kind of thinking, I'm going to launch a poll question. Start looking at equation 2 here. Which component is the acid? All right, we'll go about 10 or 12 more seconds. Go ahead and put your vote in. Okay, I'm going to end the poll. All right, let's see what everybody said. Okay, the dominant answer is HPO4 with a -2 charge. But we had all the other answer choices selected as well. So I think I need to clarify some things here. The acid and the base will only be labeled on the reactant side. Okay, so you should not have picked any of the products as the acid or the base. Okay, the acid and the base are always going to be on the reactant side. So that narrows it down to HOH minus and HPO4 with a -2 charge. All right, so I'm going to erase my little markings right here to see what happens. So we got OH minus. On the product side, which one does OH minus correspond to? It can't be PO4 minus 3. So what happens to OH minus is it becomes H2O. So it gained a hydrogen ion. You see that? So HPO4 2 minus becomes PO4 minus 3. It loses the only hydrogen that it has. All right, and it becomes PO4. So if it loses, we say it donated a hydrogen, gave it away. So for that reason, it is kind of out of space here, but this is I'm gonna zoom in, this is the acid. Right, which makes OH minus the base. Does that help make sense? So for anybody who selected the other options, don't be defeated or discouraged, okay? Again, this stuff is confusing until you start to practice it and work it out. But we're just identifying which thing gave away hydrogen. You've got to look at the reactants and the products, but you're only choosing from the reactant side what your acid and your base is. Okay, let's do the last one together. We got HCO3 minus. So this is bicarb, a bicarbonate ion, and we got water. Both have lone pairs, both have hydrogens. So which one's the acid and base? I don't know until I look at the product side. What I see is that CO3 is also right here in this compound. So these compounds correspond. So it was HCO3 and now it's H2CO3. So it gained an H plus. You guys see that? There was only a subscript of 1 and now there's a subscript of 2, an understood 1. So if it gained a H plus, it received a hydrogen, that has to make it the base. We said base is received. And it went from a negative to a neutral. There's no charge on that. Remember we said bases increase in charge. So that means water, here's the corresponding pieces, H2O and OH minus. It lost an H plus. So this has got to be the acid and the bicarb is the base. Okay, questions on this? Anybody just like so confused right now? If you're confused, somewhat get it, okay. If you're still totally lost, there will be some practice problems on this. Definitely on chapter 10 homework, which I will be launching today. I don't think I'm going to get to do it on my office hour, but we'll practice some more and let me know, reach out to me. Okay, we're going to talk about, I think, the last big topic for today, which is conjugates. Okay, a conjugate. So here's the deal. When an acid and a base react, the result is a weaker acid and base. And what I mean by result, okay, when I say the result, I mean the products. The products are the result of any chemical reaction. Okay, so the products are a weaker acid and base. So let me read these two statements. The acid that results, so, okay, so on the we're talking about the things on the product side now. Do not look at the reactants for this. But the acid that results, so it's on the product side, from the base is called the conjugate acid of that base. The acid that is produced on the product side Originally, it was the base on the reactant side. Now on the product side, we call it the conjugate acid. Okay, because it received a hydrogen. And if you have a hydrogen now, that means you could also turn around and donate that hydrogen back. So you could be an acid in that sense. The base on the product side, the base that results from the acid, is called the conjugate base of that acid. So what we have just defined are what we call conjugate acid-base pairs. Conjugate acid-base pairs. So here's a generalized equation, an acid-base reaction. Excuse me. Where we have the base written in blue here with the lone pair. There's no hydrogen on this molecule. It's just B for base. No hydrogen is represented, so it cannot be an acid. We see the lone pair, and then we have the acid, and this is the reactant side, right? All right. On the product side, and this is all nicely color-coded for us, this was the acid on the reactant side. And when it gives this hydrogen away, what's left over? These electrons, by the way, so there's 2 electrons in this bond, right? These electrons both stay on that hydrogen. So that's what we see right here is now we got a lone pair. Doesn't that look an awful lot like a base? Awful lot like a base? A base has a lone pair and no hydrogen, and that's what we have now. The leftover portion of what was the acid has now become a base itself. It's just a weaker base. Okay. And then the base on the reactant side, once it accepts, it's going to grab this hydrogen from the acid because that's what bases do. They accept hydrogen ions. So now we draw the base bonded to that hydrogen ion that it took from the acid. We see that it has a plus charge now because bases increase in charge. And this is now could be an acid, okay? The lone pair is used up, but we have a hydrogen. We could turn around and donate that to somebody. That makes me an acid if I'm a proton donor. So it's just a weaker acid, all right? So the product side is what you're going to label as the conjugate base and the conjugate acid. So if I said label your conjugate base and label your conjugate acid, you're going to label the products. If I said label your conjugate acid base pairs, you would write these things in all across. You would identify the reactant and the product that are paired together. Okay, the base and the acid, and you see this line that we've drawn between them. We're identifying that as the conjugate acid base pair, and then the acid and the base here. This is the conjugate acid base, the acid and the conjugate base pair. Okay, we kind of drew those connecting lines to identify which reactant and which base, or which reactant and which product are paired together. All right, this probably still seems a little confusing, so we're going to practice it some more. I want you to first, before we put it in an entire chemical reaction, I just want you to practice visualizing or predicting. We're going to predict what is the conjugate base for each of these following acids. Okay, so what does an acid do? Acids are H+ donors. So they're going to give away a hydrogen, and then what's left over is now going to become the conjugate base. So essentially you're drawing, remember that word disassociation? You're going to draw the disassociation reaction. And in doing so, you will produce the conjugate base. So it's all of these are going to give away an H+, right? They're all going to give away. So you could go ahead and write that if you want. So what's going to be left over on this first one? Once I give away hydrogen, what's left over? ClO4, what's the charge on it? Is it just ClO4?
Negative.
A -1. And this right here, I would highlight it now, but I'm scared to highlight anything because I don't know if I'm going to see it. That's the conjugate base, okay? That is the conjugate base. Okay, let's do the next one. What's left over after H2S, hydrogen sulfide, gives away a hydrogen? Ashton says, HS. And what's the charge on it? Yep, Grant with a minus. Okay, both of those were neutral, so the leftover, the conjugate base, is -1 charge. But this time we're starting with a positive charge. So you have pH4 plus. When it gives a hydrogen away, what's left over is going to be what? Ashton, you're like 90% right. pH3.
It would be a neutral charge.
It would be neutral, okay? It was a plus. Remember, it just decreases by 1. It just gave away 1 hydrogen. So it goes from a +1 to neutral. So we're not going to write any charge on that. And then lastly, we got HCO3 minus. So it's going to give away hydrogen. What's going to be left? Okay, it's got to give away a hydrogen. Okay, you guys so far are writing giving away an oxygen. We don't want to give away an oxygen. We want to give away a hydrogen. So Kristen, it should be just, so literally you could just mark that out if you wanted to and see what's left. It should be CO3, but the charge changes. Kristen wrote it, it goes to a -2. So everything we wrote in blue, plus the one I underlined in blue up there, those are the conjugate bases. Okay, so the conjugate base is always reduced in charge by 1. Make sense? All right, let's look at it from the opposite direction. What is now the conjugate acid for each of these following bases? So each of these compounds are now, hold on, Grant said, why did it go to a -2? Does anybody want to help fill that before I just jump in and answer it?
There was already a -1, so you're just subtracting another positive charge.
So look real close. That's perfect, Bailey. Look real close, Grant. If it's a -1 over here, basically the product side has to add up to equal the reactant side, okay? So if we have a -1 on the reactant side, we got a +1 on this hydrogen. So +1 and what is going to give you a -1? Okay, a -2. Okay, so if this was a -1 overall, and it gives away a +1, what's left is a -2. It gave away something that's positively charged, so it itself goes down in charge by 1. Did that answer your question, Grant? If it doesn't, you can tell me. I can try to explain it a different way. Okay. Y'all are always so polite. Sometimes I fear that you're like, yes, it answered, because I just don't want to be that person that says, no, I don't still understand. And I hate that. I know it's hard to, I hope it helped. All right. What is the conjugate acid for each of the following bases? So now we're just going to write each of these receiving a hydrogen. Okay, that's what bases do, right? So when we add an H plus, because that's what a base does, what do we make? We make the conjugate acid. So I want you to kind of try to work ahead of me. What are you going to make? And consider also how the charge will be affected. Ashton says we got CN-, so we're going to make HCN. That's exactly right. And you see how it's a -1 and a +1. So that adds up to neutral. So our conjugate acid here is neutral. All right. What about the next one? SO4 with a -2. Once it receives a hydrogen, y'all are crushing this conjugate acid base thing. All right, HSO4 with just a minus. Okay, water, if it is a base, receives a hydrogen. Yes, H3O plus. We had a neutral and a +1, so the conjugate acid there overall is +1. Okay, what about this last one? HCO3 minus with a H plus. Ashton, you're quick on these. H2CO3, and it's going to be neutral overall. So these are all the conjugate acids of those original bases. All right, so that was really good practice. Now we're going to put in a word problem. This is what you usually find on like your homeworks and exams, right? And for some reason, the moment you throw things in a word problem, it becomes harder. All right, so it says hydrogen sulfide ion, HSO3 minus is amphiprotic. Okay, there's this word that I was trying to address earlier when Bailey asked that really great question about losing or gaining. Amphiprotic, what does that mean? Something that is amphiprotic can give or receive a hydrogen ion. Okay, so essentially, if we put it in simple terms here, can act as an acid or a base. All right, it could do either one. Bicarb is a great example, and it's a great example for one that heavily relates to health science. Okay, anybody know why bicarb is so important to us?
pH balance of our blood, the bicarbonate system.
Mm-hmm. You guys already learned about that in some other classes? Okay. This guy has a hydrogen. It could give that hydrogen away. But it can also, look, we just wrote, he can also receive a hydrogen and make carbonic acid. Okay, amphiprotic. Can act as a, just had a test over it. Well, good. All right. We're going to look at, after we talk about pH on, what's today? Thursday. Today's Thursday, is that right? So after we talk about pH next Tuesday, next Thursday, our last day of lecture on this chapter, we're going to talk about the blood buffer system. And we're going to get all kinds of crazy with the blood buffer system and how that functions. So let's go back to this problem though. Hydrogen sulfide ion, HSO3 minus, amphiprotic. Write an equation for the reaction of HSO3 minus with water. Okay. And I want the ion to be the one that's acting as the acid. So A, here's what I mean. We're going to react HSO3 minus and water. Okay, these are our two reactants. I want you to write the products. Well, how do you know which one's the acid and the base? Well, I'm telling you here in this case, the ion, okay, this is the ion. This is the one that's going to be the acid this time. So what products will you get? So water, especially these lone pairs here on this oxygen, this is going to be the base. Okay, if the other one's the acid, this is the base, is going to grab the hydrogen. And what's left is SO3. What's the charge on it? Grant said -2. Good. And then when water receives that hydrogen, you're going to get H3O plus. H2O to H3O plus. Write this out with us. Come on, be writing it with us. Write it on your paper. All right, part B. Now I want you to write an equation for the reaction of HSO3 minus with water. This time the ion's going to be the base.
Is this
So
going to be like, all chapter 10 homework is, or is there more to it?
There's more.
Oh no.
Don't cry. Is this bad? Is this terrible? Is this like so confusing right now?
Excited because I was like, wow, this is so fun.
Well, I'm glad you're just having so much fun right now. I didn't detect any sarcasm in that at all. But no, we're going places. You know chemistry, it can never be this simple, can it?
Apparently not.
All right, so now this one's going to be the base, and this one's going to be the acid. Okay, so what that means is these oxygens are going to have lone pairs, and they are going to grab an oxygen or a hydrogen off of water. So now when that happens, we'll get H2SO3. It's going to increase in charge, so it's going to be neutral, just like what Ashton wrote. And then we're going to get OH minus. Gabby says, why don't you open the homework when we have finished the whole chapter? Kristen said, so we can work a little at a time, okay? You should be able to go through and click on a question, but not submit your answer. Is that the case on the homework? You could click on a problem. You can read it and be like, oh, haven't talked about that yet. I'm not going to work it. Go through and find the ones. That's what I encourage you to do. That's why I open it and give people different time. Just because I know people have kids, have families, people have jobs, people have lots of things going on. You guys, some of you, this has been like one of the hardest semesters of your lives. So if I open at the very, very end, you know, you'd feel like in a panic and a crunch. You have to go back and remember everything we talked about a week ago. We're not going to cover buffers till a week from now. So I get it. I totally get it. You have a lot to do. But if you try to do it little by little, that maybe will help prevent anybody from having to do all 20 problems or all 30 problems in one night. Okay. I think that's where people can panic and freak out. And it is really hard that way. So I think if you tried to just click through and do the 5 or 6 problems on the homework that apply to conjugates and identifying acids and bases and get those done, that's not the grade you finish with. You can always come back and work the next few later on. Okay, so that's what I suggest, and that's why I do it that way. I totally understand that people would prefer different things, but just because I open it now doesn't mean you have to start working it either. Okay, it's just open for those who want to start working it. So Gabby, if you don't want to start working it until we've covered all of chapter 10, you know, more power to you. You can work it however you want to work it. But I'm opening it for those who do want to start it early. So yeah, if it stresses you out to start working it, you don't have to. By the way, don't leave yet. I have an important announcement that I realized I forgot earlier. If you want to take advantage of this little bonus opportunity and do the eval, that's going to be up to 5 bonus points. And I need proof that you did it though, right? Because otherwise I don't know who did it or not. So can you, I actually had one person already send me like a screenshot, or once you complete an eval, it should send you some sort of, does it send you an email, or does it just a screen that says you completed the eval? Anybody help me out with that? You could take a screenshot of it and send it to me as proof that you did. I don't want to see what you responded. Okay. It's anonymous, and that's how I want it to be. Okay. You don't get an email. Okay. At the end, it says completed. Just a screen. Yeah. Okay. So ignore I said you don't get an email, but once you complete the eval, you should just see the screen that says you completed it, and it should say Kim 1402 or whatever. Just send me some sort of proof that you did the eval. Does that make sense? That way I can give you all the points for that.